Section 10.2 is on contingency tables. Section 11.2, excuse me, is on contingency tables. The basic concepts of testing for independence are to use a contingency table or two-way frequency table. It's a table consisting of frequency counts of categorical data corresponding to two different variables, one to categorize the rows, the other to categorize columns. And we can run a test of independence. It tests the null hypothesis that in a contingency table the row and column variables are independent, no dependency between the row variable and the column variable. The contingency table requirements for this are the sample data are randomly selected, sample data are represented as frequency counts in a two-way table. Every cell in the contingency table, the expected frequency E is at least 5. The null hypothesis is that the row and column variables are independent. Alternative is that the row and column variables are dependent. The test statistic is chi-squared is equal to the sum of observed frequency minus the expected frequency squared divided by the expected frequency, with r minus 1 times c minus 1 degrees of freedom. So r is the number of rows, c is the number of columns. And based on that, E is the row total times the column total divided by the grand total. The test for independence of the contingency table are always right-tailed. O is the observed frequency and E is the expected frequency. And if the observed and expected values are close, the test statistic is small and the p-value is large. If the observed and expected values are far, the test statistic is large and the p-value is small. If the p is low, the null must go, which then, if that was indeed the case, with the p-value being small, then we would have dependence as opposed to independence. So, for example, the contingency table has 4 rows and columns down here. The cells in the table contain frequency counts. The frequency counts are the observed values and the expected values are shown in parentheses. The row variable identifies the treatment used for a stress fracture in a foot bone, and the column variable identifies the outcome as a success or a failure based on data from the surgery unfounded for tarsal navicular stress fracture by Bruce Jansen, Internal Medicine News, Volume 42, Number 14. Find the expected frequency for the cell in the first row and first column where the observed frequency is 54. Well, to do that, we have, as I have here in parentheses, 47.478. That was calculated by taking 54 and 12 and adding those together for the row total. So 54 plus 12, this gives us a value of 66, times for the column total, we're adding up this entire success column, so 54, 41, 70, and 17, that gives us 182, divided by the complete total adds everything in here, which gives us a value of 253. Doing this will give us that value of 47.478 as the expected frequency. Using the same data as example 1 though, with the 5% level of significance to test the claim that success of the treatment is independent of the type of treatment. What does the result indicate about the increasing trend to use surgery? Here we have our random samples. So that's all fine and dandy. We have a frequency table which we were given. Now it's relative frequencies, but that's fine. Each expected frequency is at least 5. The lowest being 6. So, well, close. We could still use it. The null hypothesis is that success is independent of treatment. success is independent of treatment. And the alternative is that success in treatment are dependent. The chi-squared value that we get for this will give us a value of 58.393 with a p-value less than 0.0001. So because of this, we reject the null hypothesis. Null hypothesis of independence between success and treatment. And for the test of homogeneity, this is a chi-square test of homogeneity, a test of the claim that different populations have the same proportions of some characteristics. In a typical chi-square test of homogeneity, subjects are randomly selected from the different populations separately. In conducting a test of homogeneity, we can use the same notation requirements, test statistic, critical value, and procedures, with this exception. Instead of testing the null hypothesis of independence between the row and column variables, we test the null hypothesis that the different populations have the same proportion of some characteristics. Testing the hypotheses with contingency tables requires that every cell have an expected frequency of at least 5, and we use Fisher's exact test, used with a 2x2 contingency table with one or more expected frequencies below 5. It provides an exact p-value, not an approximation. Non-approximation is a very complex calculation, though. So, for example, the Mythbusters show on the Discovery Channel tested the theory that when someone yawns, others are more likely to yawn. Methods in this section should not be used because of the cells having an expected frequency of 4.480, which violates the requirement that every cell must have an expected frequency of at least 5. Using Fisher's exact test results in a p-value of 0.513. So there is not sufficient evidence to support the myth that people exposed to yawning actually yawn more than those not exposed to yawning. For testing the claim of no difference, the p-value is 1, indicating that there is not a significant difference between the two groups. And MCNEMAR'S test for matched pairs uses a 2x2 table consisting of frequency counts that results from matched pairs, where the frequency counts within each matched pair are not independent. We can use MCNEMAR'S test for the null hypothesis that the frequencies from the discordant categories, or discordant or different categories, occur in the same proportion. The general format for summarizing results from data consisting of frequency counts from the matched pairs. There are 2 different treatments applied to 2 different parts of each treatment. The total number is A plus B plus C plus D if the data is in a table like this one down here. MCNEMAR'S test requires that the frequencies are such that B plus C is greater than or equal to 10. The test is a right-tailed chi-squared test with the test statistic of chi-squared is equal to the absolute value of B minus C minus 1 squared divided by B plus C with 1 degree of freedom. So, for example, a randomized controlled trial was designed to test the effectiveness of hip protectors in preventing hip fractures in the elderly. Nursing home residents each wore protection on one hip, but not the other. The results are summarized down here in this table. Based on the Journal of the American Medical Association, McNemar's test can be used to test the null hypothesis that the following two proportions are the same: the proportion of subjects with no hip fracture on the protected hip and a hip fracture on the unprotected hip. The proportion of subjects with a hip fracture on the protected hip and no hip fracture on the unprotected hip. Using the discordant different pairs with the general format from what we saw in the last slide, we have b is equal to 10, c is 15. So the test statistic is calculated as absolute value of b minus c minus 1 squared divided by b plus c. So absolute value of 10 minus 15 minus 1 squared over 10 plus 15. This gives us a value of 0.640. With the 5% significance level and degree of freedom of 1, referring to the table in the back of the book A4 to find the critical value of chi-squared of 3.841 for this right tail test, the test statistic of chi-squared is 0.640, which does not exceed the critical value of 3.841. So we failed to reject the null hypothesis. The p-value is also 0.424, which is greater than 5%. Let me know if you have any questions or concerns. Thank you.